So let's look at the real forces now. We did the Coriolis as I don't know why zoom came up. Coriolis as a function of latitude approximately equal to f0 plus beta y, where beta is the variation of Coriolis in the latitudinal direction. So either we assume f0 as the constant Coriolis, and in which case we would be writing equations on an f plane, or we make f a function of latitude, linearize it and approximate it as a beta plane, where we are taking into account variations of Coriolis with latitude. Moving on to the real forces, so the denominations of the pressure and of the shear stress for derivation of the pressure gradient accelerations and friction accelerations, these are the real forces we have to consider for our governing equation. So we have a unit volume of delta x, delta y, delta z that we are considering. So let's look at the x direction first. So px is acting in the positive x direction on the left interface. Px plus delta x is acting on the right interface, but because pressure is always compressing, we have px plus delta x going in the negative x direction, so it's the difference that's going to act on this delta y, delta z interface. Similarly, you have shear forces, you have minus txz at the z interface and txz acting at z plus delta z here, so that gives you this shear. And in the horizontal you have minus txy at y, so on this interface, on the interface facing you, and txy times y plus delta y at an interface away from you. So here we have delta x, delta y, delta z, and at the surface or at the bottom you're going to have txz acting. Think of wind forcing the surface or the bottom friction dragging on the bottom surface. Okay, those are the kind of forces we have to worry about in the real part of the forcing. So mass times acceleration is rho delta x, delta y, delta z is the volume. So that gives us mass times ax, acceleration in the x direction, which is a net forcing of px acting at delta y, delta z, left interface, minus px plus delta x, delta y, delta z at the right interface. So the difference is the net x directional pressure force, and the shear forces are txy at y plus delta y interface away from us, minus tau xy at y towards us, and they are acting on the delta x, delta z interface, so delta x, delta z interface, so it's this shear. And on the delta y, delta x interface, we have a tau x z acting, and then okay, here I don't know why I'm bumbling on this one. So tau xy, y plus delta y acting on delta z, delta x, minus tau xy at y acting on delta z, delta x, plus the other shear tau xz, z plus delta z on the top acting on the delta x, delta y, minus at the bottom tau xz at z times delta x, delta y. Only at the surface or the bottom we have the term corresponding to tau x z that we will worry about. Okay, so how do we write these tau xy and tau xz? We will use the examples of eddy flux densities. Rho denotes mass density, rho s is the particle or mass density of salt that we looked at in chapter 3. So we were writing fluxes as u prime rho prime bar. So we parameterized it as minus k grad rho bar. So we were doing time mean, and this was the transient eddies, if you will. So the mass eddy flux density was minus k grad rho bar, time mean density. We did similar thing for heat, and for the y momentum we wrote it as a flux of rho u prime u bar u prime y. So this is in every direction vector, time mean of that, and we could parameterize it as minus rho k grad u bar y. So the idea was that we don't know the covariances and the eddy diffusivities or eddy viscosities, so we write it in terms of a parameterized eddy diffusivity or eddy viscosity represented by k. Using this notation that we introduced before, we can write tau xy as minus rho u prime v prime. So the eddy covariance between eddy component in the zonal and meridional directions give us the shear in the meridional, so tau xy. You can think of this as going in the y direction, which is the meridional direction. Similarly, we have in the z direction, so we can write tau xz similarly as minus rho u prime w prime bar. So as you remember from the introduction of eddies, u prime averaged over time is 0, w prime averaged over time is 0, and so on, based on our definition of transient eddies. But the multipliers u prime v prime and u prime w prime terms will not go to 0 if they are correlated and the eddy covariance is non-zero. If they are completely uncorrelated, of course they goes to 0. So in that with that, now we can write acceleration in the x direction as minus 1 over rho dp dx plus 1 over rho tau del tau xy or del y plus 1 over rho del tau xz or del z. So what is the shear in the x direction? What is the shear in the z direction? Similarly for ay, acceleration in the y direction is a similar term, minus 1 over rho dp dy plus 1 over rho del tau x del x plus 1 over rho del tau y z del z. And in the z direction it is minus 1 over rho del p dz plus 1 over rho del tau zx over del x plus 1 over rho del tau zy del y minus the gravitational free fall acceleration that we expect in the z direction. Some of you can already see this and recognize the hydrostatic balance, in which case these terms are only important at the surface or at the bottom. In the interior of the flow, away from the frictional interfaces, hydrostatic balance holds. Minus 1 over rho del p del z minus g will be 0. That's the meaning of assuming that the vertical terms are negligible. Vertical acceleration term is negligible. So that's what we are doing here for hydrostatic balance, which is a strong constraint and is valid pretty much in all situations in the ocean and the atmosphere, except where there are deep convections happening, where deep water is forming in the ocean, or deep convection in the atmosphere, where very rapid vertical motions are happening to produce precipitation and clouds and so on. So acceleration in the x, then minus 1 over rho dp dx plus 1 over rho del tau xz del z. Ay is minus 1 over rho del p del y plus 1 over rho del tau yz del z. And in the z direction we have minus 1 over rho del p del z minus g. So going back to our equation of motion, du dt is apparent or inertial forces plus the real forces. Putting those in, so du dt then becomes the pressure and the shear forcing plus the Coriolis plus Fv. So you can look at the sign and how the Coriolis appears. In the zonal momentum equation we have plus Fv. So the meridional velocity determines the Coriolis in the zonal direction, and zonal velocity determines the Coriolis in the meridional direction. So dv dt is pressure, the shear, and Coriolis. In the vertical we have dw dt is minus 1 over rho dp dz minus g. So if the vertical accelerations can be ignored, neglected, because the fluid is very shallow and the large scale horizontal motions are much larger than the vertical, then you can assume that minus 1 over dp dz is equal to minus g, which basically tells you also that if you have initially no vertical shear in the velocities, then they must continue to be so, because in the vertical we have to satisfy the hydrostatic balance. So that's kind of a constraint that emerges out of the hydrostatic balance. So we will take this further by writing it in the form we saw before in 6.3, where dA dt, the material derivative, Lagrangian derivative, total derivative, is written as partial A partial t plus the advection term u dA dx v dA dy plus w dA dz, and that gives us with these terms du dt plus u du dx plus v du dy w du dz equal to minus 1 over dp dx plus 1 over delta xz del z plus fv. So this is basically the Navier Stokes equations for the planetary flow, in this case the ocean, even though we are carrying rho, because in the ocean usually we end up assuming the water is incompressible and rho can be held constant except when it appears in the vertical, especially with g. Okay, so similarly in the meridional direction we have dv dt plus u dv dx plus v dv dy plus w dv dz equal to minus 1 over rho dp dy plus 1 over rho delta yz del z minus fu. So dw dt, vertical acceleration, plus u del w del x v del w del y w del z w del z equal to minus 1 over rho dp dz minus g. We will take these and add continuity equation to it, because this is not a complete set yet. We have to worry about mass conservation. In the third chapter we derived the advection equation as d rho dt equal to minus grad dot u bar u vector rho. So this is a dot product. If rho is constant and ocean is incompressible, then this reduces basically to this term going to 0 and divergence of u becoming 0. So a incompressible fluid is non-divergent, so du dx plus dv dy plus dw dz equal to 0. So you can imagine that if u and v are initially not varying in the vertical, then this also gives you some special relations, as we will see later on. Okay, so now we have the equations we need for starting to think about the solution to large-scale ocean. Of course, we also need the thermodynamic equation or density relation in terms of temperature and salinity, and we have similar equations for temperature conservation, salinity conservation, and so on. But first, we will not worry about those and just derive shallow water equations to see what kind of solutions come out of the shallow water equations and what is meant by a shallow water. I think you can imagine that water is too shallow compared to the horizontal scales. It's always relative. You cannot just assume shallow water equation without comparing it to the horizontal scales, and it's relatively small in the vertical compared to the horizontal scales. Okay.